So we continue. I promised another property of ideal such which is similar to the property to be a prime or irreducible, prime in the case of integers, irreducible in the case of polynomials. We now want the second equivalence 1 and 2. So as in the first case, we got equivalence between 1 and 3 here. So that would be, that was first, and now it is second. Definition. An ideal M in the ring R. So we call R is a commutative ring with identity here. Again, the inclusion is strict, not the whole ring, is said to be maximal. If the following property holds: whenever J is an ideal in R such that J is in the middle between the ideal M and the whole ring R. Then J equals M or J equals R, not both. For an obvious reason, M and R are not the same. So what happens here? The ideal is called maximal if there are no ideals in between this ideal and the whole ring. The whole ring is, of course, an ideal in itself, a trivial one. So there is no ideal in between which contains R but is contains M but is contained in R. So no, the meaning is no ideal J such that both inclusions are strict. such an ideal does not exist. We cannot find an ideal which is strictly bigger than M, strictly contains M, and at the same time it is not R itself. It is maximum, meaning no ideal except the trivial one contains M. So again, let me first demonstrate that this property generalize, the property being a principal ideal generated by prime. So for a prime which is an integer, the ideal the principal ideal generated by this prime is maximal. Indeed, let there be an ideal J which is in between the whole ring, which is the ring of integers in this case, and our ideal, principal ideal generated by P. Assume that P is not J. What does it mean? J contains P and some extra. There exists some element of the ring which is an element of J but not an element of this ideal, the principal ideal. So J is slightly bigger. It contains something which is not in the ideal. What does it mean that M is not an element of this principal ideal? This means that M is not a multiple of P. These are all multiples of P. M is not a multiple of P. We know that we can reformulate that as P does not divide M. Now, P does not divide M, and P prime and P prime imply, these two conditions imply, as we discussed in detail earlier, that the greatest common divisor of P and M is 1. Indeed, P does not divide M, so the only possible common divisors should be divisors of M, of P. P is prime, so it's divisible by itself plus or minus, and plus minus 1. But M is not divisible by plus minus P, so plus minus 1 are the only common divisor among them. The greatest common divisor is, of course, 1. And by our alternative characterization of the greatest common divisor, that means that a linear combination of P and M, AP plus BM, is 1 for some integers A and B just integers. Now, P is inside J. The whole ideal, all multiples of P, are elements of J. J contains the ideal P, therefore it contains all multiples of P. Let me write it this way. Implies this is MAP is a multiple of P. All multiples of P are elements of J. So AP is a multiple of J. At the same time, M is an element of J by absorption property of an ideal. J is an ideal. Any multiple of M is also an element of J. Thus, that implies Bm is an element of J by the absorption property. These two of J. These two together, J being an ideal, is a subring. So these two together, AP is an element and BM is an element of J. J is a subring, so their sum is also an element of J. AP plus BM is an element of J. Thus, but this is 1, thus 1 turns out to be an element of J. That implies J is equal to Z, because together with 1, by absorption property, J contains all multiples of 1, which are all integers. So what did we prove? We proved that if our assumption was P is not equal to J, then J is not equal to P, then J must be equal to Z. So the assumption J is not P, it contains an extra, implies J is all Z. Thus, the ideal P is maximal. There is no bigger ideal except Z itself. So, in the course of the proof, we used here 1 is inside an ideal, therefore the ideal is the whole ring. This is quite a general statement, which I would write down just as a byproduct, which may be useful in many situations. if I will write it as a proposition if you want, if an ideal I in R, a commutative ring with identity, is such that it contains a unit such that there is a unit of R there is a unit U of R which is an element of I, then I is the whole ring. The proof is more or less immediate. Unit is invertible, so there by definition of unit, there exists U inverse. So U inverse U is the identity in the ring. At the same time, and U inverse U belongs to I by the absorption property. Of I. That's embedded into the definition of ideal. You remember, element of ideal times any element of the ring is again an element of ideal. Thus, the identity of the ring is an element of the ideal. Again, by absorption property, of I for any R, any element in the ring, R times identity, or write it other way around, it's clearer. R is equal to R times identity, and this, by absorption property, is an element of ideal. Thus, any element of the ring is an element of the ideal. As claimed, ideal is equal to the whole ring. Here we have one, but for a unit that also works. This is just a by the way remark. So an argument similar to what we did here is available, and you can easily restore it for on an irreducible polynomial, same argument with the greatest common divisor, with very slight changes, applies. Again, not a factor of irreducible polynomial is relatively prime to the irreducible polynomial. Again, we have an alternative characterization of the greatest common divisor. And again, we have that, after all, that identity of the field in that case belongs to the ideal, therefore everything belongs to the ideal. So now for the maximal ideals, we have theorem 615 in the book, which is equivalence of 1 and 2 in the theorems 2.8 and 5.10 we started with. Let M be an ideal in R. The definition of maximum ideal includes, let me convince you, that maximum ideal is never the whole ring. Would be too easy. This is maximal for everything. We throw it away and search a maximum among proper ideals. So let M be an ideal in our ring R, a commutative ring with identity. M is maximal if and only if the quotient ring is a field. The theorem is proved cleanly in the book. I can add nothing to that proof, so I skip that. Look it up in the book. That is the second analog of principal ideal generated by a prime or irreducible polynomial. An immediate corollary 6.16 tells us that every maximal ideal is prime. Indeed, in our ring R, the ideal is maximal, therefore the quotient, the factor ring, is a field, but every field is an integral domain. Thus, this quotient is integral domain, and we apply the previous theorem. Where it is? We apply the previous theorem. This one. An ideal is prime if and only if the quotient is integral domain. For maximum ideal, this is integral domain, therefore the ideal is prime. So every maximum ideal is prime, and the easiest way to do that is to combine theorem 615 and theorem 614. So, proof, combine, theorem 615, theorem 614, and the fact which we proved in the past somewhere, that every at the very beginning when we discussed the definition of rings, fact that every integral, every field is an integral domain. Another consequence, we considered a counterexample. Now we can immediately benefit from that. So, not example. Not every prime ideal is maximal. Indeed, as in the example above, we consider the ring R to be the ring of polynomials with integral coefficients, and we consider the ideal I as we took previously. We know that we already discussed above that the factor ring, the quotient, is isomorphic to Z, and Z, the ring of integers, is an integral domain but not a field. From theorem now theorem 614 allows us to conclude that this ideal is prime. The factor is integral domain. And theorem 615 allows us to conclude that this ideal is not maximal. In the ring, because the factor ring is not a field. In fact, we could see that directly, although it is a lengthier calculation. For example, but that is a lengthier argument. We can find an intermediate ideal. This ideal is a subset of the ideal generated by 2 and x with 2 generators. We already discussed this example before. This ideal is actually maximal. But this ideal is maximal, but does not contain 1. It is not the whole ring. So we discussed this ideal in detail as a finitely generated ideal, which is not principal. As this was an example of a finitely generated ideal which is not principal. Now it is an example of an ideal sitting exactly in between this ideal, which is prime but not maximal, and the whole ring. So the ideal X is indeed not maximal. To prove these inclusions is not a difficult but much lengthier, still much lengthier exercise than we just did, claiming that using the two pretty powerful theorems. That is all I wanted to tell you about chapter 6, and in chapter 10 we will discuss some more subtle properties of commutative rings with identity. Namely, we will return back to the fundamental theorem of arithmetic, and we will see how it may fail in some rings and how it cannot be provable by the same method as we did in some other rings. Thank you for listening.